Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to be discussing the electric potential. In our prior two lectures, we discussed the electric field. We calculated it two ways. The first way was using just a knowledge of the volume charge density or surface charge density or line charge density, and basically we didn't make any assumptions about the symmetry of the problem. The second technique we used was Gauss's law, and in that case we had to make use of the symmetry of the problem, and as it turns out, Gauss's law always holds, but it's not always useful as a practical matter, and we saw that only if you had systems of high degree of symmetry could you use Gauss's law to solve those problems. But when Gauss's law works, it works very fast. So just as a reminder, the electric field is equal to 1 over 4 pi epsilon naught times the volume integral of the volume charge density times the separation vector over the magnitude of the separation vector cubed. And notice we are integrating over the prime coordinates, which is what we should do because we're integrating over the source to arrive at a solution for the electric field at some observation point or some field point. As should it become quickly apparent, this expression gets very difficult to use if you have anything but a system of high degree of symmetry. And even when we did investigate certain systems like charged shell, for instance, there was a lot of work involved. There were a lot of steps, a lot of algebra, and of course the more algebra you have, the greater the chance there is of making a mistake. We solved that same problem using Gauss's law, and because of the symmetry of the problem, we were able to do that. And Gauss's law gave us a solution very fast. So Gauss's law tells me that the flux through a closed surface is equal to the amount of charge contained within that surface divided by the permittivity of free space. So when we had systems of a high degree of symmetry, you could find a surface such that I could pull E out of this integral and just basically calculate the surface area, and from that determine what the electric field is at certain points. Another useful way of expressing Gauss's law is in differential form. So just a brief digression here. The divergence theorem from vector calculus tells you that if you have some arbitrary vector A, doesn't have to represent anything at this point, and you calculate the surface integral of that vector over a closed surface, that is going to be equal to the volume integral of the divergence of that same vector. So what this enables me to do is to replace the left-hand side of Gauss's law with the volume integral of the divergence of the electric field. And then I have my right-hand side. So now I've got two volume integrals that are equal to each other. Left-hand side, divergence of the electric field. The right-hand side, 1 over epsilon naught volume integral of the charge density. Since this expression has to hold for arbitrary volumes, it can't depend on the size or shape of the volume itself, the integrands must be equal to each other. And that's Gauss's law in differential form. And we'll find this to be very useful in the coming weeks. So just a brief digression there, and let me get back to the electric potential now. I'm going to calculate a line integral. line integral over some path that goes from R1 to R2 of the electric field. So say I start at R1, wind up at R2, and here's my charge Q, and I want to calculate the line integral of the field due to this charge along this path. Well, the electric field due to a single point charge is just equal to Q over 4 pi epsilon naught R squared in the R direction, the radial direction. I'm going to take my line element and write it in terms of spherical coordinates. And the line element is r caret dr plus theta caret r d theta plus phi caret r sine theta d phi. However, I'm taking the dot product of the electric field, which only goes as a function radially, and so therefore the only surviving term is going to be the dr term. Okay, do the math. I want to get the result that I get a scalar, of course, and that my integral is just equal to the difference between two scalar quantities, one evaluated at R1 and one evaluated at R2. Another point that I want to observe about this is that since the only thing that matters are the endpoints, the only thing that matters where I start, where do I end, if I happen to take this integral and calculate it over a closed loop, so in other words, I go from here to here and back to where I started, that line integral vanishes. The circle again indicates that we are calculating this integral over a closed path. An equivalent way of saying this is that the curl vanishes. And fields that have this property are conservative. So in electrostatics, our electric field is conservative. To see that the curl vanishes by inspection, let's just write the curl of Q over 4 pi epsilon naught R squared R caret, and I see since I'm the only contribution I have is a function of R in the R direction, the curl has to vanish because the curl gives you contributions curling around, not going radially. So that's 0 by inspection. Okay? So I'm going to define an integral now. I'm going to take line integral of the electric field from some reference point up to some observation point R, and take the negative of that as well. What does a reference point mean? Well, that means a point at which the electric potential is 0. This is my electric potential. That's where it vanishes or where it can be assumed to vanish. And the interesting thing about potentials is that the only thing that matters is the difference between 2 points in space. It doesn't matter what the value is in itself. If somebody says, oh, I calculated the electric potential, it has value 10, you have to know with respect to what, and that's where the reference comes in. As we'll see, oftentimes it's convenient to take the reference with respect to infinity. Other times that will not work at all, and you have to figure out some other point in space that makes sense or is convenient. So let's look at VR1 and VR2. So take the difference between these two potentials. If I think back to my vector calculus class, I can make use of the fundamental theorem of gradients. Which tells me for some arbitrary scalar function, and let's just call it f for now, take the line integral of that's gradient of a scalar, that's just equal to that function evaluated at the endpoints. So by making use of this expression, I can draw a conclusion on the way E, the electric field, is related to my potential V, another way of expressing it other than this form. See that E is equal to minus the gradient of the potential. And if I look over the left-hand side of the board, I deduce that the curl was equal to 0, it's vanished. But if you remember from vector calculus, whenever you take the curl of any gradient, that has to vanish. So because this curl of this vector is equals to 0, that tells us the electric field has to have a very specific form, tells us the electric field has to be equal to minus the gradient of the potential. write my two equations over here. Again, your potential is defined as the line integral minus the line integral of the electric field from some reference point to some arbitrary observation point. And the electric field can also be deduced from the potential by this expression. It's just equal to minus the gradient of the potential. And just as a reminder, the gradient in Cartesian coordinates just has this form. And look at the spreadsheet that I posted to see the gradient in the spherical coordinates and also for cylindrical coordinates as well. And once again, the meaning of this is that the gradient tells you the rate of change of a scalar quantity and also the direction of the rate of change, maximum rate of change of that scalar quantity. Some features I want to point out. Of my potential. Number one, it sounds an awful lot like the potential energy. And just be aware, it is not the same thing. It's a different physical quantity. Remember, potential energy is measured in units of joules. Our electric potential is measured in units of volts. It's not the same thing as potential energy. We'll get to the definition of the potential energy in an upcoming video, but just be aware it's not the same thing and has units of volts. Number two, the potential is a scalar. And what we'll see is that we can extract information about behavior of distribution of charges, and we can investigate that scalar quantity, the potential, as opposed to the electric field. Now, why is that an advantage? Well, it's a scalar, so it's only got one component that we have to deal with. With an electric field, you have three dimensions to handle. So this makes the calculation a little bit easier for certainly a variety of systems. Number three, it obeys the superposition principle. So in the same way that we could calculate the electric field due to a set of charges, just sum up the contribution from each charge, we can also calculate the potential due to a summation of individual charges. And last but not least, reference is arbitrary. The only thing that matters with the electric potential is what it is with respect to some position in space, or with respect to some point in space, not just its value by itself. So that's a distinction between the electric field and the potential. So with this in mind, I'm going to go ahead and calculate the potential for a variety of charge configurations. The first one I'm going to do is just for a point charge. In fact, we really already solved this problem. Electric field due to a point charge is just Q over 4 pi epsilon naught r squared, r caret, and we're dotting it to r caret dr, blah, blah, blah. We don't need to put the rest of that up there because this is only a term that's going to contribute. And the other question is, where do we take our reference? Well, the convenient place to take it is at infinity. So I do math here. I wind up with Q over 4 pi epsilon naught r. Remember, our definition of potential is minus the line integral from some reference to some arbitrary r of the electric field. So when we integrate this, we wind up with the minus sign, so we've got minus minus. This is evaluated r. That's just going to be Q over 4 pi epsilon naught r. And the second term, of course, is just going to vanish because we're taking that with respect to an infinity. So that is my potential. Now let's say that you've got two charges. And let's suppose these two charges lie along the x-axis. And we'll sketch the y-axis up there. And they're equidistant from the origin. And we have the same magnitude of charge, both positive. So what's my net charge, net potential going to be then? Well, in this case, my charge is moved over from the origin. So this first one gives me a contribution of Q over 4 pi epsilon naught magnitude of the separation vector r minus ax. So in other words, we're calculating our potential up here. So it's here to here. My second contribution is for my second charge. That also has positive value. And it's Q over 4 pi epsilon naught r plus ax cubed. If you're more comfortable writing this out in terms of the Cartesian coordinates rather than leaving this as an r, we can write this out. So r minus ax is equal to square root of x minus a squared plus y squared plus z squared. And magnitude of the separation vector between r and the second charge up here, r plus ax, is equal to square root of x plus a squared plus y squared plus z squared. And then my potential becomes Q over 4 pi epsilon naught square root of the sum of the squares, in this case x minus a squared plus y squared plus z squared. And the second term is Q over 4 pi epsilon naught square root of x plus a squared plus y squared plus z squared. Now, let's say that we take the second charge equal to b minus q. How does everything change? Well, it just becomes a minus sign over here. And a minus sign over here. So now we're taking a positive charge and a negative charge. You want to evaluate what your electric potential is along the midplane. In other words, what is it at x equals 0? Well, by inspection, what you'll have here is this term will just be given a squared, and this term over in the second term will also give an a squared. So therefore, these terms will cancel out. So therefore, along the midplane at x equals 0, my potential vanishes. at the moment, it just seems like, well, that's an interesting observation, but why is it useful? Well, we're going to get into a technique called the method of images. And the neat thing about the method of images is that you can replace more complicated looking problems with image charges. And now you can solve electrostatics problems a lot easier than you might have thought possible. And that in turn leads to an even more powerful technique using Green's functions, which is usually handled at the graduate level, not at undergraduate EM, for solving electrostatics problems. Okay, so that's the potential due to two charges. Let's look at the potential due to some charge continua. Let's take a look at a parallel plate capacitor. Suppose that the distance between these two plates is d, and let's suppose further that I've stuck surface charge density sigma on the top plate and my sigma on the bottom plate. Definition of a capacitor is, or rather, two conductors that hold equal opposite charges and maintain a potential difference between them. Now, we investigated the electric field due to charged sheets, and we found that in between those sheets, the electric field was just uniform. It's just equal to sigma over epsilon naught. That's the same answer you get for parallel plates. So in this region, now let me write it over here so it's a little clearer. The electric field is sigma over epsilon naught, and in this case, the way we've drawn our plates, it's going to be oriented downwards and the minus sign. And the electric field vanishes outside. The question here is, what's my potential between these two plates? In this case, we're going to integrate from here to here. So therefore, we're not taking a reference at infinity this time around. We're going to take a reference on the bottom plate. We're going to say, well, that potential is equal to 0. From the bottom up to the top. And we wind up with sigma d over epsilon naught. I wanted to calculate the potential at some arbitrary point between these two plates. So in other words, I don't want to go just from here up to here, but here to here, some point z. Then my potential becomes sigma over epsilon naught z. So whereas my electric field is uniform between the plates and it's pointing downwards, my electric potential increases linearly as I go from the bottom plate up to the top plate. Now, I should emphasize that the plates we're talking about here are assumed to be very large. So we're assuming plates are very large. Okay, and why do we have to do that? Well, because our electric field will be uniform here. What if you didn't assume that your plates were very, very large? Let's say that they were finite in size. Why does that matter? Well, the thing we know about electric fields is if I take the line integral around a closed path, the electric field has to vanish. other words, let me erase this here. So I draw a little rectangle here, and my path goes down here, here, up, and then to the left. And if I were to go from inside to the outside, I'd see, well, the top and bottom don't contribute because they're perpendicular to the direction of the field. The line of elements here, I mean, one's pointing to the left, one's pointing to the right. Dot that into z caret, those vanish. Now, the left-hand side certainly contributes, right? We wind up with a sigma epsilon naught z caret and minus, basically we're going to write it with minus z caret dz. So essentially we'll wind up with a sigma L over epsilon naught from the left-hand side. If we assumed that our plates were finite, something has to happen over here. And our electric field lines don't just go straight down and then vanish outside. We actually have what is called a fringing effect. So your fields actually look like this outside of the finite size plate. And why does that happen? Well, it's because of the nature of the electric field that the line element has to, closed loop has to vanish. That wouldn't be the case if your electric fields were uniform just inside and went to zero directly outside. So you'll see some distortion in here close to the edge as well. But for all intents and purposes, we stick with very large parabolic plate capacitors to avoid that little sticky problem. Now let's look at the line charge now. And let's say that, let's make this very long. And I want to figure out what's the potential of this line charge with respect to some point in space. Electric field due to a line charge, calculated that a couple of ways. One way was using knowing what the line charge distribution looked like, and another way was using Gauss's law. And here we have that's equal to lambda over 2 pi epsilon naught as in the s direction. My potential then is going to be minus from some reference to some observation point. And since we're doing cylindrical coordinates, it's convenient to use cylindrical line element. Just as a reminder, dl here is equal to s caret ds plus phi caret s d phi plus z caret dz. But just as before, when we were calculating the potential due to a point charge, all those other terms dropped out. The only term that contributes is this first one, and that'll give me s caret dot s caret is just 1, and this is minus lambda over 2 pi epsilon naught, and here we'll wind up with the natural log of evaluated at some point s minus minus or plus lambda 2 pi epsilon naught natural log of s reference. So if you thought to yourself, well, gee, let's take the reference with respect to infinity, that seems like that might be a good choice. You can see that would not, because natural log of infinity blows up. You have the same problem at, if you thought to take the reference with respect to the position of the line charge itself. That also blows up. So we have to take a reference somewhere else. Where should you take it? Well, it's wherever it's convenient for the problem. Remember, the only thing that matters with electric potential is the difference between 2 points, difference in potential between 2 points, or with respect to a point, not its value itself. So this I choose, again, for whatever's convenient, okay? Now let's take a look at the old charged sphere problem again. Or a charged spherical conductor. And I want to figure out what's my potential. Well, I've got 2 regions that sit base, basically. I've got the exterior solution and the interior solution. Well, we figured out before that when we were inside, the electric field vanishes in this case. When you're outside, the electric field just goes as Q over 4 pi epsilon naught squared in the R direction. I'm going to calculate my potential first in the exterior region and then in the interior region. In this case, it's useful to take my reference with respect to infinity. That leaves me with Q over 4 pi epsilon naught R, and once again, the only thing that matters is the distance from the center. And this potential actually looks like all the charge were concentrated at the center of the sphere. And just as a reminder, sigma and Q are related to each other. Sigma equals Q over 4 pi big R squared, where capital R is the radius of the sphere. I want to take my calculate my potential inside. I need to break this interval into 2 parts because my electric field differs from inside and outside, or inside and outside. First term going from infinity up to the radius of the sphere. And then from the radius of the sphere into the interior region, so somewhere way out here. First of all, I calculate from here to here, and now calculate from here to here. But notice the second term vanishes. Why? Because my electric field vanishes there. So what that tells me is that my electric potential is equal to Q over 4 pi epsilon naught R, capital R, anywhere inside the sphere. So the surface of my sphere is an equal potential. And at any point inside that sphere, my potential has the same value. Why? Because my electric field vanishes there. If I had potential that varied with position, I would no longer have a curl-free electric field in the interior, or electric field that vanishes. Let's take a look at a uniformly charged sphere this time around. Has volume charge density rho. Inside, of course, the electric field does not vanish. But it has value of rho r over 3 epsilon naught. And if I wanted to write that in terms of Q, that would be equal to QR over 4 pi epsilon naught r cubed. Exterior solution, electric field is Q over 4 pi epsilon naught r squared in the r direction. In both cases, the electric field goes out radially. Outside, again, it's like all the charge is concentrated at the center of the sphere. Inside, of course, the electric field is different. Only at the center of the sphere does the electric field vanish. So we calculate the electric field or rather the potential in both areas. Let's look at the exterior solution first. We're going to go from infinity, so we're taking a reference point up to some point outside. Outside, we know that our electric field is just Q over 4 pi epsilon naught r squared. I do the math here, and I wind up with Q over 4 pi epsilon naught r. Again, the only thing that matters here is the distance from the center of the sphere, and once again, it looks like all the charge is concentrated at the center, just as we saw for our charged spherical conductor. For our interior solution, we have to break this integral into two parts. First term, of course, we're going to go from somewhere out in infinity and integrate it to the surface of the sphere. And